I'm back. And first, I want to apologize for not making any videos for quite, gosh, it's been what, like a little over 2 years now? And, I just got busy and, had a lot of projects to do and just didn't have time to make videos. So, I'm back. I'm going to be making more videos coming up here. I'm going to start right now by kind of going over what I've been up to over the past 2 years and kind of catch everybody up and also kind of go over where things are going to be going. I am going to be starting the project I've been talking about, where from beginning to end I'm going to take a concept and really, you're down there moving the camera, homie? So yeah, we're going to do that. So let's get started, and I wish you would stop moving the camera. And we'll start with the RAM tester and where that's gone. So let's go on over and let's take a look at that. Okay, so here we are. I'm going to kind of run through the evolution of the tester. So here we have the original 5101 RAM tester, and I based it around a PIC 16F884 running at 8 megahertz. Here we have the SIF socket, and then we've got LEDs indicating whether each bank is good or bad. And this was okay, but I kept getting people asking me, hey, can you do one for this RAM chip, or can you do one for another RAM chip? And so the next evolution was this one right here. And this is when I first added in the 5 switches, and each switch would select a different test. Again, we're still sticking with the 884 here. We're still using the same LED scheme as we did in the first version. Added more LEDs, broke it up into smaller chunks of memory to indicate whether that was good or bad. And I actually was including a 9-volt power jack with these at that time. Well, the problem here was it was confusing. Because you had to hit a different switch to select a particular test, and then you'd have to look at the LED to figure out, oh, well, what test did I select? So I wasn't terribly happy with this design either. So we evolved. Now, I don't believe this version made it out too much. I don't think I made too many. I did sell some. We've added a DC power jack. You can select either 5-volt input, which bypasses the voltage regulator, or you can do 12-volt input and use the onboard voltage regulator, which is the preferred configuration that I recommend. Added relays to control power consumption to the chips. So now we can actually test chips with a higher current requirement. And just reduced it to 2 switches, where you just push this button to select the type of RAM you're going to test, and then test the RAM. Still confusing for some people. There's a limited amount of information that you can pass on using just LEDs. And also at this point, I upgraded the design to the PIC 16F1519, which has more memory, can run at 16 megahertz on the internal oscillator. So it was able to basically cut testing times in half. Here we have the first iteration of the RAM tester with an LCD screen, which informational wise solved a lot of problems. This particular version is running with a 16F884 in it, but I had intended to upgrade to the 1519, so this was just for prototyping and testing. We've added the 5 buttons to allow easier control of the tester. There's no ZIF in here because this was actually kind of scrapped almost right after I built this up for the first time, and I just wasn't really happy with the design. As you can see, you have to use a 9-volt battery for one, and I really didn't like this even from the very beginning. But, you know, all the basics here, you use the arrow keys to go through the different tests. And if we actually do a test here, we'll see that it, of course, failed because there's no chip there to actually test. So now let's move on and take a look at the LCD tester that is currently available, and we'll go over all of the parts and stuff with that and see what changes I made to make things better. Right. Here we have it. This is the currently available RAM tester with the LCD screen, and let's go over some of the features that I decided to go with this, and well, why. So first off, we can see it's got a PIC 16F1519. We have a 5-volt voltage regulator. We have added an on-off switch, which is something I really love, because now it's a piece of cake to turn the unit on. And we have this ZIF. Now when I designed this, I really was looking at, look, okay, one of the things I really want to do is keep the user's fingers away from this voltage regulator at all times. I didn't want them having to come up here and hit any buttons to work the ZIF or anything like that, because on long tests this guy can get quite warm and maybe even hot enough to cause discomfort. I do have the switch here, but kind of figured, you know, you're still pretty far away from that voltage regulator when you're turning the unit on and off. I have the ZIF here, the LCD screen, and then the buttons arrangement was changed to this design here. So we've got our up down arrows, left right, and then our test button here. If we go through this, there's actually quite a lot of tests that are in the unit. And one of the other nice features about this is when you turn the unit off and you turn it back on, it's going to power up on the exact same test that you powered down on. So if you were testing 5100 RAMs, you didn't have time to finish your batch, and you turn the unit off, you come back, you turn it back on, it's all set to go. You're right there where you left off. So let's do a quick test here, and we can see the difference in the bad test displayed information. Now if we go ahead and scroll through this, we can see which bits are bad, the starting address, and the number of addresses that it detected bad on that pass. So let me talk about some of the problems with this design. Now, you know, as I said, sticking to the theme where I was trying to keep as much of the circuit away from the areas that the user was going to have their hands, I was still limited in the design. And we've got a relay here for power and a relay here for pin 14 on the ZIF. Any chip, any RAM chip that's smaller than 28 pins, the ground is running through the PIC 16F1519. Now what that means is that if that RAM chip is pulling more current than the 1519 can supply, the 1519 is going to shut that bit down. And the chip will be untestable. Okay, so let's go ahead and actually test the chip here and see what the heck we got. So I'm going to go ahead and set that up to 5101. Open the ZIF up. Go to 5101. Make sure I've got the notch over here on the same side as the lever. Push test, and boom. We know the IC is okay. So we can take a look at a longer test now. And this one's going to display different information. So that's going to show us the pass number, what it wrote, what it read, and come back and say, hey, yeah, that chip's okay. It passed. Everything's good. It's a great, great, great little tester. I mean, the feedback I've been getting from the community is they really love it. But it has limitations. Now, one of the design problems with this tester, and I outright apologize for this. I should never have done it. It just, you know, I was just trying to make it as user-friendly and configurable as possible. And in the process, I created a serious flaw. We do have a DC power jack here. We've also got a jumper right here. This jumper was intended to allow the tester to run from either a unregulated power source or a regulated 5-volt power source. And the problem that some people were coming across is they were using both. They would sometimes power it from unregulated, and they would sometimes power it from regulated, which means they're changing this jumper. The problem with that is the second you plug this guy in to a voltage greater than, like, I guess 6-7 volts, and this is set to the 5 volt position, kiss your tester goodbye. It's going to destroy the micro, this guy here, the screen, the voltage regulator. Everything gets damaged. I really wish, thinking back on it, I hadn't done it quite this way. So that's one of the issues I wanted to fix in the next iteration of this board, was to change the power configuration so that you can't blow the board. So right now I'm working on a new design, a new tester that eliminates all of the issues. Okay, here it is. This is the new tester design. It solves so many problems that I was having with the other design. It fixes so many issues. And basically what we've got here is a modular design. So this is the base unit. The base unit has a card edge connector. It has a 12 volt regulator. It has a 5 volt regulator. LCD screen. It has got a port expander chip. It's got a 40 pin ZIF socket, which allows it to test larger size chips. And the whole idea behind this guy is to be modular, to eliminate a lot of the problems I was having before. And this right here is the SRAM blade. And as you can see, the whole design is called the Inquisitor. And basically, because of the modular design, these little blades allow this guy to do almost anything you need it to. So I'll go ahead and plug the blade in. We will turn it on. And as you can see, it starts right up. We've got a lot more chips in here to test. I'll kind of run through them. And they all work. Also added a bicolor LED here on the side. This was a hack job. This was something I added in after I had designed the first iteration of the main board. So let me kind of go run through this. And as you can see, I mean, for the most part, the LCD screen, the switches and everything are in the same spot as the previous design. We've removed the serial to parallel chip, and we've added a port expander. The port expander runs LCD screen and also runs this bicolor LED. The code's not finished yet, so I'm going to quickly run through here, and yeah, there we go. So we can see the LED here is lit up orange, failed, and then when it sees the fail, it turns red. In the final version, this LED is actually going to be right in here. This is where this whole design is cool. Like I said, we got a 40 pin ZIF here. And what that means is we can now test, and because of the blade system, we can turn this guy off, pull our blade out, and put in our prototype PIA blade tester. So we plug that in, we power back up, and now we've got the PIA blade tester ready to run. And I happen to have a chip here. Okay. Now this code is not complete, so we're only going to actually test parts of the PIA. I haven't quite finished it yet. But let's go ahead and run through. So we're checking port A first, port B, and then we're checking our interrupts to see if they're working correctly. And that's about as far as it goes. I still have some more stuff to test there and to get that up and running. And as you can see now, instead of being confined to the tester and having to completely redesign a board and include the screen, the chip, and all this other stuff, anything that is common to all the testers is contained on the main board. Everything that's specific to a tester is contained on the blade. Now let me kind of go over some things here. There's actually a couple of LEDs down here. And if I turn that on, the top LED is going to light up nice and bright. It says that's a card error. Which means there's not either the card's plugged in incorrectly or it's not there at all. Now if I take the blade and plug it in backwards, and believe me, it's been designed to do this, we'll also get the card error. But this guy has been designed to be plugged in backwards and not take damage. So we'll pull the board back out, put it back in, and as you can see, it's fine. Same thing with the PIA tester. Hold on. Designed to be plugged in backwards. We can see there's a card error. Oops, let me turn that off. Pull the board, plug it in right. And as you can see, we're fine. We can go ahead and run through the test again and prove that it is working correctly. There we go. So now there's another LED here, and that's where this jumper right here comes in. Now the 12 volt side of this is designed to either be powered by a regulated 12 volt supply or a unregulated. And right now I've got it set to unregulated. So I'm just going to kind of pop that over there and we'll power this on. The other LED lights up. It's not quite as bright, but it is definitely there. And that's telling you that the voltage is greater than 12 volts. And that indicates, oh, there's a problem. All right, that's it for now. Thanks for watching, and be sure to subscribe.